Okay, let's unpack this. When you get into a modern vehicle, you're trusting it with your life. Think about it. Hitting the brakes, the airbags deploying, even just, keeping you in your lane. These aren't just mechanical marvels anymore. They're incredibly complex electrical and electronic systems, what we in the industry call EE systems. And behind that trust is a whole world of invisible, meticulous safety engineering. Today, we're taking a deep dive into the very backbone of that engineering. ISO26262, specifically focusing on Part 10, which gives us the general guidelines for functional safety in road vehicles. It's not just some dusty rulebook, it's a living, breathing framework designed to prevent harm from electronic system malfunctions.
Absolutely. And what's truly fascinating here, I think, is our mission to guide you through the core development processes within this functional safety lifecycle. We'll trace the journey of safety, from the very first spark of an idea, that concept phase, all the way through to the nitty-gritty of hardware and software development. The profound insight here is understanding how these stages aren't isolated islands. Not at all. Instead, they form this deeply interconnected chain, each link crucial, all pulling together towards one paramount goal: ensuring safety for everyone on the road.
That's absolutely it. And for you, our listener, whether you're, gearing up for a big meeting, trying to catch up on this critical field, or maybe you just have that insatiable curiosity, this deep dive is designed to be your shortcut. We're here to distill these often intricate details, offering those genuine aha moments without ever making you feel, overwhelmed by the sheer volume of information that's out there. We want you to walk away not just informed, but genuinely enlightened. So, ready to pull back the curtain, let's get started. So if we're going to engineer safety into something as sophisticated as a modern car, where do we even begin? It definitely doesn't happen by accident.
Right. No, absolutely not. It all starts with a very structured, systematic approach to development. Think of it like building a skyscraper. You don't just start laying bricks. You need blueprints, foundations, a clear plan.
Right.
Exactly. In automotive safety, this systematic approach is often visualized as a V-shape. It guides development from those high-level requirements, diving down to the most granular implementation details, and then meticulously climbing back up through integration and validation. We call this the reference phase model, or more commonly, the V model.
The V model, okay.
Yeah, and the V model is much more than just a diagram. It's the fundamental principle ensuring functional safety is designed in from the very start. It's not an afterthought or something you try to, patch in at the end.
So it's baked in from day one.
Precisely. Imagine starting with a broad, high-level understanding of what the vehicle needs to do safely. That's the top left of the V. As you move down that left side, you progressively break down those high-level ideas into increasingly granular details. The initial concept, then system development, followed by the specifics of hardware development, and finally software development. Each step gets more precise.
Down into the weeds, basically.
Kind of, yeah. Then, as you move up the right side of the V, you meticulously integrate and verify everything. You test individual software components, then integrate them with the hardware, and finally test the complete system within the vehicle itself. This upward journey ensures that every single detail aligns perfectly with those initial safety requirements defined way back at the start.
Okay.
And throughout this entire process, there are continuous management and auxiliary processes supporting every phase, keeping everything aligned and on track. This systematic approach is really about building confidence at every single step that the final product will be safe.
That's a great visual. And when we talk about that initial concept phase, the very top of that V, what's the absolute first step? How do you figure out what could possibly go wrong in a vehicle with all these complex electronic systems? I imagine it's not just a simple checklist.
You're absolutely right. It's anything but simple. This is where hazard analysis and risk assessment, or HARA, comes into play. It's truly the foundational activity in the concept phase. Its main purpose is to systematically identify and classify every potential hazardous event, every single one that could be caused by a malfunctioning E system. And then crucially, to formulate the top-level safety goals to prevent or mitigate those risks. It's where you shift from thinking generally about safety to, pinning down the specifics of failure.
Okay, HARA. So how does that process actually work?
The HARA process is highly structured. It begins with hazard identification. And this isn't just brainstorming. It's a systematic determination of all the potential hazards. Hazards that could arise from any malfunctioning behavior of the vehicle's electronic systems. You have to consider every operational situation, every operating mode where a malfunction could lead to a hazardous event.
Every situation. Even weird ones.
Well, within reason. This includes not only the correct intended use of the vehicle, but also any reasonably foreseeable incorrect use. For instance, think about a driver accidentally hitting the wrong button or, trying to do something unexpected. To aid this, engineers often leverage structured methods like FMEA failure mode and effects analysis, or HAZOP, hazard and operability studies.
Okay.
And a very real example of a hazard identified at this stage could be something like unwanted release of energy from a device that can result in an explosion. That's a very tangible, very serious hazard that demands a systematic response.
An explosion. Wow. Okay, so once you've identified these potential hazards, how do you actually quantify or categorize their severity? Because like I said, a flat tire is pretty different from, say, unintended acceleration.
Exactly. That leads us to the next critical step, hazardous event classification. For each identified hazardous event, you classify it based on 3 key parameters: severity S, exposure E, and controllability C. These 3 factors combine to give you a comprehensive picture of the risk involved.
Severity, exposure, controllability. SEooC. Got it.
Let's break those down. Severity, or S, is an estimation of the potential harm. Harm to anyone involved, the driver, passengers, or even other road users. The standard defines 4 classes. S2 means no injuries at all. S1 indicates light to moderate injuries. S2 signifies severe or life-threatening injuries where survival is probable. And S3 is the most critical for life-threatening injuries where survival is uncertain, or even fatal injuries.
S3 sounds pretty bad.
It is. So going back to our example of the unwanted release of energy that could result in an explosion, if that explosion is assessed to lead to life-threatening injuries for the vehicle's occupants with survival uncertain, that would unequivocally be classified as an S3. It's really about understanding the potential human cost of a malfunction.
Makes sense. And what about exposure? How do you estimate how often a car might even be in a situation where one of these hazards could occur? That seems like it could vary wildly.
That's a crucial point. Exposure, or E, estimates the probability that a vehicle will actually be in an operational situation where a specific hazardous event can occur. We have classes from E0 to E4. E0 is for, well, incredible situations. Think an airplane landing on a highway or a major natural disaster. These are typically excluded from further analysis because they're just beyond the scope of reasonable design.
Right, act of God territory.
Sort of. Then E1 is for very low probability, E2 for low, E3 for medium, and E4 for high probability of exposure. And this isn't about how many vehicles are sold, it's about the likelihood of a specific driving scenario happening. For example, if you're analyzing a scenario where the vehicle is, say, driving at less than 15 kilometers per hour, and traffic data suggests this condition occurs a moderate percentage of the total driving time, let's say between 1% and 10%, that would typically be estimated as E3. It's about the vehicle's context during operation, not its market share.
Okay, context matters. And finally, controllability. This sounds like it refers to the driver's ability to react, but what if they can't?
Precisely. Controllability, or C, is an estimation of the probability that the driver or other road users can actually avoid the harm once the hazardous event occurs. It ranges from C0, meaning controllable in general, to C1, easy to control, C2, normally controllable, and C3, difficult or downright uncontrollable.
C3 sounds like you're just along for the ride.
In many cases, yes.
Yeah.
This is about the window of opportunity, or lack thereof, to prevent harm. For our unwanted release of energy example, if an explosion happens, the ability of the driver or passengers to control that item failure and the resulting explosion is considered implausible. That would clearly place it in the C3 category.
Right.
Now, what's really nuanced here is that external measures, even other systems in the car, can influence controllability. For instance, if a vehicle with an automatic gearbox always engages a gear when the key is off, a sudden unintended release of an electric parking brake might not cause a hazardous event because the car can't easily roll away. But if it's a manual transmission left in neutral on a hill, that same EPB release becomes a much higher risk due to lower controllability. You see,
Yeah, the overall vehicle state changes the risk. Interesting.
context matters immensely when assessing risk.
So once you've got these 3 classifications, severity, exposure, and controllability for a particular hazardous event, how do you combine them? What's the final output of this HARA process that, guides the rest of the development?
That's where the automotive safety integrity level, or ASIL, comes in. And ASIL is determined for each hazardous event by combining its S, E, and C classifications. And this raises, I think, a really important question. What do these levels actually mean for the engineering process itself? What kind of impact do they have downstream?
That's the core of it, isn't it? The ASIL. So ISO26262 defines 4 distinct ASILs, right? From ASIL A, which is the lowest safety integrity level, moving up through ASIL B, ASIL C, and finally ASIL D, which represents the highest, most stringent safety integrity level.
Correct. And there's also a category called QM, or quality management,
Yes, QM.
where the specific ISO26262 requirements aren't strictly applied because existing quality management processes are deemed sufficient to manage that particular lower risk.
And we use a specific ASIL determination table, sort of like a lookup chart, to map these SE and C classifications.
Exactly. It's a matrix defined in the standard.
So for our unwanted release of energy example, with its S3 severity, E3 exposure, and C3 controllability, if you look that up in the table, it leads directly to an ASIL C. Is that right?
That's typically how it works, yes. It provides a systematic, objective way to assign a required rigor level to each potential hazard.
Rigor level, I like that.
And this is where the profound impact of the ASIL truly reveals itself. Once determined, the ASIL dictates the necessary rigor and intensity of all subsequent development activities. A higher ASIL, like ASIL D, means significantly stricter requirements for design, demands far more rigorous development methods, and requires exceptionally high levels of verification and validation effort.
So ASIL D is like the gold standard maximum effort. Essentially, yes. This heightened rigor applies uniformly across system, hardware, and software development. It permeates everything. It's not just about a single component. It's about the entire life cycle for that safety goal. Think of it this way. ASIL D implies an almost zero tolerance for certain types of failure, demanding everything be done with the utmost precision and scrutiny. And if you find yourself with multiple safety goals that are similar or interconnected, the rule is you always assign the highest ASIL among them to the combined goal.
Take the highest one.
This ensures that the most stringent safety measures are always applied, leaving no stone unturned in the pursuit of safety. The ASIL is truly the driving force behind the entire safety engineering effort for that function.
So the ASIL essentially becomes this numerical representation of risk, which then dictates the engineering effort needed. Makes sense. But how do these ASIL classifications and the HARA results get translated into those very first concrete design parameters? Where does the design actually start? That's where safety goals come in. They are the direct output, the immediate product of the HARA process. They represent the top-level functional safety requirements for the item being developed. Think of them as overarching high-level objectives that define what needs to be achieved to prevent or mitigate those specific hazardous events identified earlier.
Can you give an example?
Sure. If unintended airbag deployment is identified as a hazardous event during aero, the precise safety goal derived from that might be: the airbag system shall only deploy the airbag when a vehicle collision occurs that requires airbag deployment. Clear, specific.
Very precise.
They have to be incredibly precise and unambiguous. They often specify the necessary safe state the system must achieve or maintain in the event of a fault. For example, if a fault occurs in an electric parking brake system, the safety goal might dictate EPB function shall be disabled to prevent unintended engagement or release while driving. These safety goals define the acceptable boundaries for risk and serve as the guiding star, the ultimate target for all subsequent design and implementation efforts across the entire development lifecycle. They are the first articulation of what safe actually means for this specific item or function.
Okay, so we've navigated the concept phase. We've done the HARA, identified hazards, assessed risks with SE and C, determined the ASILs, and clearly defined our top-level safety goals. Now we move from the abstract, the concept, to the truly concrete. How do we take those high-level safety goals and start architecting a safe system? This brings us to product development at the system level, right?
Exactly. This is where the engineering really begins to coalesce, to take shape. The flow is incredibly logical and systematic. Those overarching safety goals we just discussed, identified in the concept phase, they directly inform the functional safety concept, FSC.
FSC.
The FSC is absolutely critical because it specifies what the system needs to do from a safety perspective. It defines the necessary functional safety requirements. It outlines the safety mechanisms and other safety measures needed to achieve those safety goals. It also starts identifying the high-level system architectural elements, the big building blocks that will support these requirements. It's the very first step in outlining the functional behavior that is absolutely indispensable for safety.
So what needs to happen for safety?
Precisely. Then, building on that, the functional safety concept drives the creation of the technical safety concept, PSC.
TSC. Functional, then technical.
Right. Well, the FSC defines what needs to be safe. The TSC gets far more specific. It details how that functionality will be implemented at the system level. Crucially, it starts allocating responsibilities between hardware and software. It translates those somewhat abstract functional safety requirements into concrete, actionable technical requirements. This is where you might decide, for instance, that a specific safety function needs redundant sensors, or that a certain calculation must be performed by two independent microcontrollers.
Okay, so how? Can we use the airbag example again?
Absolutely.
Yeah.
Let's revisit the airbag. The FSC might specify a high-level requirement like, the system shall have a redundant function to reliably detect whether the vehicle is in a collision. That's the what's. But the TSC would go much deeper, defining how this is achieved. The implementation shall include two independent accelerometers with different axial orientations, and two independent firing circuits for the squib, with the airbag only deploying if both acceleration signals meet the criteria simultaneously and are verified by independent logic. You see the difference?
Yeah, much more specific. It's the actual technical implementation details.
Exactly. This transformation from what to how is absolutely fundamental to system-level safety design. The TSC ultimately defines the overarching system safety requirements, SSRs, and lays out the entire system architectural design. It's the blueprint.
The detailed blueprint, got it. And once you have that blueprint, how do you ensure that all these different parts of the system, hardware, software, communications, buses, don't inadvertently interfere with each other, especially when safety is on the line? That seems like a huge risk.
It's a critical challenge, absolutely.
Yeah.
And it's addressed by ensuring that the system design is developed in strict accordance with those technical safety requirements derived from the TSC. This involves meticulously specifying all interfaces between system elements, essentially, defining precisely how they talk to each other and ensuring that these interactions are strictly controlled. A cornerstone principle here, really fundamental concept, is freedom from interference.
Freedom from interference.
Yes. This means meticulously designing the system so that a malfunction in one part, maybe even a non-safety critical part, cannot inadvertently affect a safety critical function in another part. Imagine if a glitch in the infotainment system, like the radio, could somehow interfere with the braking system controller. That's precisely what we aim to prevent through careful architectural design and partitioning.
Makes sense. Keep things separate and protected.
Exactly. And during this design phase, a fundamental activity is performing safety analyses. These aren't just checkboxes. They're deep dives into the design to scrutinize its integrity, its robustness. Their purpose is multifaceted. They provide crucial evidence that the design is suitable for its intended safety purpose. They help identify potential failure causes and their effects throughout the system. They confirm which elements are truly safety-related and need special attention. And they rigorously verify the effectiveness of the safety mechanisms that have been proposed in the TSC. It's a continuous feedback loop during design.
So you're constantly checking the design against the requirements. What kind of analysis methods are used?
For these analyses, the standard highly recommends using both deductive analysis and inductive analysis, especially for higher ASILs like C and D, where the risk is greater.
Deductive and inductive. Okay, what's the difference?
Deductive analysis is essentially a top-down approach. You start with an undesirable event, say unintended acceleration, and ask, what could possibly cause this? Fault tree analysis, or FTA, is a prime example. It systematically breaks down that top-level hazardous event into its contributing component failures or error conditions, creating a logical tree-like diagram.
Starting from the bad outcome and working backwards.
Exactly. Conversely, inductive analysis is a bottom-up approach. You start with a component, maybe a sensor or a microcontroller, and ask, what happens if this specific component fails in various ways? Failure mode in effects analysis, or FMEA, is the classic example here. You systematically look at every possible failure mode of each component and trace its effects upwards through the system to see if it could lead to a hazard.
So starting from the component failure and seeing where it leads.
Right. The combination of both these approaches, top-down and bottom-up, provides an incredibly robust safety net. It gives engineers different perspectives on potential failure paths, helping to ensure nothing critical is missed.
Okay.
And beyond just identifying potential faults, the design process also heavily emphasizes systematic fault avoidance. Now, this isn't about preventing random hardware failures like components wearing out. It's about designing out errors that are inherent in the design or specification itself, human errors, basically.
Bugs in the design itself.
Correct. It means aiming for a design that promotes modularity, which makes elements easier to understand, reuse, and verify independently. It involves adequate granularity, ensuring design elements are at the right level of detail, not too broad, not too minute. And maybe most importantly, simplicity. actively avoiding unnecessary complexity in components and their interfaces, because complexity is where bugs love to hide. This often involves reusing well-trusted concepts, designs, and interfaces that have a proven track record in previous safety-critical applications. Why reinvent the wheel if a safe one already exists?
Build on proven success. Makes sense.
It's about building a robust foundation from the ground up to inherently reduce the likelihood of these subtle, systematic design flaws creeping in.
What's truly fascinating here, listening to this, is how it isn't a linear process at all. It sounds like a constant loop. If new hazards or failure modes are discovered during these detailed system-level safety analyses, or if the design itself reveals a previously unconsidered risk, you can't just ignore it, can you? You have to go all the way back, potentially, and update that initial HAR, reevaluate the SEooC, maybe even adjust safety goals and ASILs. It sounds like a truly iterative and self-correcting process.
You've hit on one of the most critical aspects. You're absolutely right. Functional safety, according to ISO 26262, is inherently iterative. Any new insight, any newly identified potential failure mode, any discrepancy found during analysis or verification means potentially revisiting earlier stages. This continuous looping back, this refinement, is what makes the process so robust. It's about building confidence, not just once at the beginning, but continually throughout the entire development journey.
Okay, now let's really dive into the nuts and bolts, or maybe more accurately, the silicon, the circuits, the actual physical components. Hardware is where many of these abstract safety concepts become tangible physical realities. This is all about product development at the hardware level.
Precisely. We're moving down the V model into the specifics of the hardware. The hardware safety requirements are meticulously derived directly from the technical safety concept, KSC, and the overall system architectural design we just discussed. These requirements are then refined further to specify precise properties of the hardware safety mechanisms. This includes mechanisms for internal fault control within the hardware itself, and also how the hardware interacts safely with the external world or other systems. And a supremely critical aspect refined at this stage is the hardware-software interface, or HSI. This document is vital. It specifies exactly how the software will communicate with and utilize the hardware resources, things like memory mapping, how timers are configured and used, how data flows through input-output ports, interrupt handling, all the details. It's the definitive rulebook for their interaction.
The contract between hardware and software.
Good way to put it, yes. And the guiding principles for hardware architectural design here are paramount, especially as you go up in ASIL levels. We're talking about things like hierarchical design, ensuring interfaces are precisely defined and minimal, and rigorously avoiding any unnecessary complexity. These steps are all about minimizing the chance of errors occurring, whether they're random physical failures or systematic design flaws.
Okay, so we're talking about the physical world now, and in the physical world, things eventually wear out or, just randomly fail. It happens. This is where it gets really interesting for the hardware side, I think. Dealing with these random failures. It's not if a component fails, but when. And crucially, how that inevitable failure is managed by the system. How does ISO 26262 classify these types of hardware faults? There must be different categories.
That's a brilliant point, because random hardware failures are an undeniable reality we have to engineer for. ISO 26262 provides crucial key fault classifications in hardware to help engineers systematically understand and mitigate these risks. It gives us a common language.
Okay, what are they?
Let's start with a single point fault, SPF. This is pretty much what it sounds like. A fault of a single hardware element that, on its own, directly leads to the violation of a safety goal. It's a single point of failure because there's no safety mechanism in place to prevent or mitigate it. Imagine an unsupervised resistor in a critical sensor circuit. If it fails open, and that directly causes a safety goal violation, like a wrong reading leading to incorrect system behavior without any backup or monitoring. That's an SPF. It's a direct, unmitigated path to risk.
The most dangerous kind, sounds like.
Potentially, yes, because it's uncovered. Next, we have a residual fault. This is a fault, or sometimes just a portion of a fault's effect, that can still lead directly to the violation of a safety goal, even though there's at least one safety mechanism designed to cover it. The issue here is that the safety mechanism doesn't fully mitigate or control that specific fault or part of it. It's a remaining, unaddressed risk, despite a safety measure being in place.
Like having a safety net with a small hole in it.
That's a good analogy. It helps, but it's not perfect for every scenario. There's still some residual risk. Now, this brings us to the particularly insidious latent dual point fault, LFM. This is a complex but crucial concept to grasp.
Latent, meaning hidden.
Exactly. An LFM is a fault that contributes to a safety goal violation, but critically, it only leads to that violation in combination with another independent fault. And crucially, this first fault, the latent one, is neither detected by a safety mechanism nor perceived by the driver until that second fault occurs. It's like a hidden weakness, a ticking time bomb waiting for a second trigger.
Wow. Can you give an example? That sounds tricky.
Sure. A classic example would be a single-bit error in ECC-protected flash memory. ECC stands for Error Correcting Code. This technology automatically corrects the single-bit error, so the system continues to function perfectly, and importantly, the error isn't signaled to the rest of the system or the driver. The system just carries on. This first error is now latent. It happened, it was corrected, but nobody knows about it. If, later on, the ECC logic itself were to fail, that's the second independent fault, then this previously corrected but unsignaled bit error, combined with the ECC logic failure, could lead to corrupted data being used, potentially causing a safety goal violation.
Ah, I see. The first fault lies dormant until a second one happens.
Precisely. It's a silent threat that only becomes dangerous when another seemingly unrelated event occurs. That's why they require careful analysis. Now, in contrast, a detected dual-point fault is a fault that is detected by a safety mechanism, and that detection prevents a safety goal violation even if the driver isn't explicitly informed. So, taking our ECC example again, if a transient bit flip is detected and corrected by the ECC before the potentially faulty data is provided to the CPU, and the correct value is written back or used, that would be a detected dual-point fault. The system handled it, the safety goal was not violated, and normal operation continued, possibly without anyone ever being aware.
Okay, so the system caught it.
Right. And finally, safe faults. These are exactly what they sound like, faults that simply do not contribute to a safety goal violation under any defined condition. This could include situations where multiple independent faults, more than 2, maybe 3 or 4, would be needed simultaneously to cause an issue, which is usually considered sufficiently improbable. Or it could be faults in components that simply have no safety impact whatsoever on the system's intended function, maybe part of a non-critical feature. Understanding these distinctions, SPF, residual, latent, detected, safe, is absolutely critical for allocating design effort and safety analysis appropriately. You focus resources on the riskiest fault types.
That makes a lot of sense. So once you've classified these potential hardware failures, how do you actually measure the overall risk from all these random hardware failures combined? Because ultimately, you need to prove that the design meets the safety goals, right? You need some numbers.
Precisely. We need quantitative evidence. That's where we use the probabilistic metric for random hardware failures, PMHF. This is a crucial quantitative analysis metric used to evaluate the overall risk of a safety goal violation due to the combination of all credible random hardware failures over the intended lifetime of the vehicle or item.
PMHF. Okay, how does that work?
The PMHF is expressed as an average probability of failure per hour, averaged over the item's entire operational lifetime. It's a key metric that's compared against very specific, extremely stringent target values defined in the standard for each ASIL. For example, for an ASIL-D system, the highest level of the PMHF must be less than 10 8 occurrences per hour.
10 to the minus 8. That's
Yeah.
tiny. One failure in 100 million hours.
It's incredibly low, yes. For ASIL-C and B, the target is slightly less stringent, but still very demanding. Less than 10 to 7 occurrences per hour, or 1 in 10 million hours. This reflects the potential severity associated with failures in these high ASIL systems.
So how is it calculated? It must consider all those fault types.
Absolutely. The PMHF calculation rigorously considers all relevant types of faults, single-point faults, residual faults, the bits missed by safety mechanisms, and multiple-point faults, particularly those dangerous latent dual-point faults. It also has to factor in exposure durations. These are things like how long a latent fault might realistically exist undetected before it's revealed by a second fault or found during routine maintenance or diagnostic checks. It considers the maximum duration of a typical driving trip and the average time until a vehicle might be brought in for repair after a warning light comes on. All these time factors influence the probability.
Wow, that's detailed.
It has to be. What's truly interesting, though, is that even if a single hardware component, say a specific chip, has a relatively high inherent failure rate based on semiconductor physics, the overall PMHF for the complete item or system can still be astonishingly low, meeting those tough ASIL targets. This is achieved through clever hardware architectural design, using redundancy, diverse components, and implementing robust safety mechanisms that effectively prevent or mitigate those individual component failures from escalating into actual safety goal violations. It really pushes the boundaries of designing for reliability and fail-safe or fail-operational behavior.
That's a staggering level of reliability they're aiming for and achieving. And to get that PMHF number down, you need to be able to detect those faults when they happen. How do engineers ensure that their safety mechanisms are actually effective at catching these various hardware failures? How do you measure detection?
That brings us to another key concept: diagnostic coverage, DC. This is a core concept supporting the PMHF calculations and the overall strategy for mitigating random hardware failures. Diagnostic coverage is essentially a measure, usually expressed as a percentage, of the extent to which implemented safety mechanisms can detect faults within a specific hardware element or a group of elements. It's estimated for both residual faults, to understand how much risk remains, and latent faults, to understand how quickly they can be detected before a second fault occurs. It provides crucial confidence in the effectiveness of the implemented safety measures. The higher the DC, the more effective your safety net is considered to be.
So DC tells you how good your fault detection is. Can you give some examples of safety mechanisms and their typical DC?
Sure. Let's look at some common hardware safety mechanisms and how their diagnostic coverage is typically evaluated. Watchdogs, for instance, are ubiquitous in embedded systems. These are essentially independent timers that monitor whether the main program is executing correctly and within expected time limits, especially watchdogs with separate time bases, not relying on the main system clock, and using time windows, expecting a signal within a specific window, not just any time, can detect issues like a system clock failure, or software getting stuck in a loop, or running wildly out of sequence. They typically offer medium diagnostic coverage for those types of faults. They're like a diligent, silent observer checking if the processor is still alive and kicking correctly.
Okay, watchdogs. What else?
For ensuring data integrity, especially over communication buses like CAN or Ethernet, information redundancy techniques like cyclic redundancy checks, CRCs, are vital. They add a small piece of calculated data, a checksum, to each message, allowing the receiver to independently verify its integrity upon arrival. CRCs generally offer medium to high diagnostic coverage for detecting data corruption bits getting flipped during transmission. However, it's important to note they typically provide less coverage for other communication errors, like messages being lost entirely, duplicated, or arriving out of sequence. The design of the CRC itself, its size, like CRC8, CRC16, CRC32, and the specific mathematical polynomial used directly affects its Hamming distance, which in turn determines its precise error detection capabilities. So a bigger, smarter CRC can detect more complex error patterns.
Makes sense. More bits, better detection.
Generally, yes. Then there's sensor monitoring. This is crucial. Simple sensor-valid range checks are a basic form. They detect things like electrical shorts to ground or power or open circuits by ensuring the sensor's raw electrical signal stays within expected physical limits. More advanced techniques include sensor correlation checks. Here, you compare readings from redundant sensors measuring the same thing, say, 2 accelerometers in an airbag control unit, or 2 wheel speed sensors on the same axle. Comparing them helps detect subtle in-range drifts, offsets, or one sensor getting stuck at a fixed value, even if that value is technically within its valid range. And even more sophisticated are sensor rationality checks. These often use diverse sensors measuring different physical properties, but which can be mathematically related or converted to equivalent values. An excellent example is in engine control, comparing throttle position, manifold absolute pressure, and mass airflow sensors. While they measure different things, they all indirectly relate to the amount of air entering the engine. By cross-referencing them using a physical model, the system can derive a consistent airflow reading and detect if one sensor is giving an output that is physically irrational given the readings from the others. This diversity helps catch not just random failures, but sometimes systematic sensor calibration issues too.
Comparing different views of the same thing. Clever.
It is. Finally, self-test by software running on the hardware can provide diagnostic coverage, particularly for processing units, CPUs, or memory. These tests might run at startup or periodically during runtime. However, their effectiveness can sometimes be limited, especially for detecting transient soft errors, those momentary glitches caused by radiation or electrical noise that don't cause permanent damage but can corrupt data or execution flow temporarily. These can be hard to catch with periodic tests. So all these quantitative analyses, especially involving PMHF and diagnostic coverage calculations, are not just academic exercise on paper. They provide crucial, measurable evidence that the hardware design meets the target ASIL requirements for random failure tolerance. And while the exact PMHF value itself might have some inherent uncertainties due to the complexities of getting accurate component failure rate data and modeling assumptions, the rigor of performing the analysis provides a high level of confidence in the overall safety integrity of the hardware design. It's a blend of meticulous design practice and statistical confidence building.
All right, moving from the physical realm of hardware, the silicon and circuits, to the, well, ethereal yet equally critical world of software. This is truly the brain of these complex EOE systems. And unlike hardware, where you're often battling those random physical failures, in software, it's often systematic faults that are the primary concern, those subtle, elusive errors introduced during design or implementation. So this section is all about product development at the software level and how rigorous design and testing help us avoid those hard-to-find bugs.
That's a key distinction, absolutely. Software doesn't typically wear out like hardware. The challenge lies in getting the design and implementation correct from the start. Software safety requirements, or SFRs, follow the same logical derivation path as hardware requirements. They stem directly from the technical safety concept, TSC, and the overall system architectural design. They specify what the software needs to do to fulfill its part of the safety goals. What's paramount at this stage is that the software architectural design must be meticulously crafted specifically to address and control systematic faults. These are the errors that sneak in during the human-led design, coding, or configuration phases, rather than being a result of random physical effects.
So how do you design software to avoid these human errors, these systematic faults?
To achieve this, the standard outlines several key principles for avoiding systematic faults in software. Think of them as fundamental rules for good, safe coding and design practices. These apply across the board, but become much more rigorous at higher ASILs. They include modularity. This means breaking down the software into small, well-defined, independent, and often reusable units or components. This makes the code much easier to understand, test in isolation, and verify. Then there's adequate granularity. This is about ensuring that the design elements, the modules or functions, are at just the right level of detail, not too abstract and encompassing too much, but also not overly specific and fragmented into tiny, unmanageable pieces. Finding that balance is key, and perhaps most importantly, simplicity. Actively avoiding any unnecessary complexity in software components, and particularly in their interfaces. Complexity is very often the breeding ground for subtle, hidden, systematic bugs that are hard to find during testing. Keep it simple whenever possible.
Modularity, granularity, simplicity. Makes sense. What about the coding itself?
Right, beyond these high-level architectural principles, defensive implementation techniques are absolutely vital when writing the actual code. This means building in explicit checks and safeguards directly into the code to handle unexpected situations or potential errors gracefully. For example, always verifying divisors before performing a division operation to prevent catastrophic division by zero errors, which can crash a system. Or checking caller identifiers or access permissions to ensure a critical function is only being called by its intended authorized source, preventing unauthorized access or unexpected behavior. Another simple but effective technique is consistently using a default case in switch statements or similar constructs. This catches any unexpected or invalid input values that weren't explicitly handled, preventing the system from potentially going into an undefined or unsafe state. It also involves performing explicit checks on assumptions made in the code and on data boundaries, ensuring array indices are within bounds, pointers are valid, input data is within expected ranges to prevent buffer overflows or crashes that can lead to security vulnerabilities or unsafe operation. And of course, strict adherence to established coding guidelines, such as MISRA-C or AUTOSAR-C++E, is highly recommended, especially for higher ASILs. These guidelines specifically exclude ambiguous, undefined, or historically error-prone language constructs that can introduce subtle, hard-to-debug flaws that might pass basic testing.
So it's about writing robust code that anticipates problems.
Exactly. And the standard also makes an important conceptual distinction here between software fault avoidance and software fault tolerance. Software fault avoidance is primarily about reducing the overall likelihood of occurrence of systematic faults in the first place. It's achieved through excellent design practices, rigorous development methods, thorough verification, and adhering to all those principles we just discussed: modularity, simplicity, defensive coding, guidelines. It's about building the software correctly, right the first time, to minimize the number of bugs introduced.
Avoid the bugs altogether.
That's the primary goal, yes. But software fault tolerance, on the other hand, is about designing the system to keep it operational, or at least fail safely, despite the potential presence of residual software systematic faults that might have slipped through the avoidance measures. This can involve more advanced techniques like implementing redundant software implementations, where the same critical function is executed by two different software modules, perhaps developed by separate teams or using different algorithms. If one fails, the other can take over, or they can cross-check each other. Or using diverse algorithms for the same safety function, where different computational approaches should yield the same safe result, providing another layer of checking. It could also involve implementing runtime self-tests within the software that can detect inconsistencies or errors, and sometimes even correct them or switch to a safe, degraded mode of operation, allowing the system to continue operation safely, even after encountering a fault. It's the art of gracefully handling the unexpected, assuming some faults might still exist.
So avoidance tries to prevent bugs. Tolerance tries to handle the ones that might still be there. Okay. But it's not enough to just design it well and use these techniques. You have to prove it works exactly as intended, even under stress, right? And that, I imagine, means a whole lot of rigorous testing, which I suspect is a real unsung hero of functional safety, especially for software.
It absolutely is. Testing is where the rubber meets the road for software safety assurance. Software testing activities are multi-layered and progressively integrated, building confidence at each step as we move up the right side of the V model. It begins at the lowest level with software unit verification. This is the verification of individual, isolated software units or modules against their specific design specifications. We check if each small piece does exactly what it's supposed to do. This phase critically includes measuring structural coverage. This involves using tools to track which parts of the code were actually executed by the test cases. Common metrics include statement coverage, ensuring every line of code is executed at least once by some test, or, more stringently, branch coverage, ensuring every possible outcome of a decision point, like an if statement, is tested. High structural coverage helps ensure the test cases are sufficiently thorough and that no significant part of the code logic remains untested.
So you know your tests actually ran through all the code paths.
Ideally, yes, or at least a very high percentage required by the ASIL. The next step up is software integration and verification. Here, those individual software units that were tested in isolation are combined into larger components or subsystems, and their interactions are rigorously verified. This ensures that the interfaces between modules work as intended and that the combined units function correctly together as a whole without unexpected side effects.
Making sure the pieces play nicely together.
Exactly. Following this, system and item integration and testing involves bringing the integrated software and the hardware together and testing the complete EE system or item. A crucial part of this phase is demonstrating the effectiveness of those hardware fault detection mechanisms, like watchdogs, sensor checks, at the hardware-software interface level. Can the software correctly detect and react to simulated hardware faults? This is often achieved through sophisticated fault injection tests, where faults, like sensor failures, communication errors, memory corruption, are deliberately introduced into the system during runtime, often using specialized hardware or software tools to see if the safety mechanisms detect the fault and the system reacts appropriately and safely according to its specification. We also use error guessing tests here, which leverage expert knowledge and experience of common programming errors or tricky system interactions to design specific tests aimed at exposing those potential vulnerabilities that might be missed by more systematic methods.
Trying to break it, basically.
In a controlled way, yes. The final comprehensive stage is vehicle integration and testing. Here, the fully integrated item, the ECU with its software, is installed and tested in the actual vehicle environment. This phase aims to demonstrate the correct overall functional performance, accuracy, and timing of the safety mechanisms at the vehicle level under real-world operating conditions. Does the system do what it's supposed to do safely in the car? This can involve extensive long-term tests that run for extended periods, simulating thousands of hours of driving cycles to uncover subtle timing issues or memory leaks. And it includes user tests under real-life conditions, which put the system through typical and sometimes atypical driving scenarios and user interactions to ensure it behaves safely and predictably in every situation a driver might reasonably encounter.
That's an incredible amount of testing, layer upon layer. But what about the tools themselves that are used to create the software? Things like the compilers that turn code into machine instructions, or automatic code generators, or static analysis tools that check for bugs. Are they just assumed to be perfect, or is there a process to ensure they're not introducing errors themselves? That seems like another potential source of systematic faults.
That's an excellent and often overlooked question. And you're right, it is a potential source of systematic faults. It brings us to the critical aspect of confidence in the use of software tools. as outlined specifically in ISO 26262 Part 8, but relevant across the life cycle. Many modern software development processes rely heavily on sophisticated automated tools for tasks like model-based code generation, compilation, static analysis, or even test execution. You absolutely cannot just assume these complex tools are flawless. They are software too, after all.
So how do you manage the risk from the tools?
The standard addresses this by requiring a systematic evaluation and determination of a tool confidence level, TCL, for each tool used in relation to safety-critical development activities. This TCL is based on two key factors. First, tool impact, TI. This assesses the potential for a malfunction or error within the tool to actually introduce errors into the safety-related elements of the final product, or, alternatively, for the tool to fail to detect existing errors in the product. TI1 means low impact potential, TI2 means high impact potential. Second, tool error detection, PD. This measures your confidence in the existing measures within your development process to prevent the tool from being used incorrectly or to detect any erroneous output produced by the tool. TD1 means high confidence in detection, TD2 means medium, and TD3 means low confidence. These two factors, TI and TD, are combined using a table in the standard to determine the overall tool confidence level, TCL1, TCL2, or TCL3. TCL1 requires basic trust, while TCL3 demands the highest level of confidence and scrutiny for the tool.
Okay, so you figure out how critical the tool is and how likely you are to catch its mistakes. What happens if it's TCL2 or TCL3?
If a tool is determined to have a TCL2 or TCL3 rating for its specific use case, then rigorous tool qualification measures are required by the standard. This means providing clear, documented evidence that the tool is reliable and completely suitable for its intended safety-related use within your specific project environment and configuration. Qualification measures can include things like a thorough evaluation of the tool manufacturer's own development and quality assurance processes. Did they build the tool safely? It might involve extensive validation of the tool's functionality against known reference test cases or benchmarks. Or you might gain increased confidence from its extensive prior use in similar safety-critical applications with a proven track record of reliability, confidence from use. Tool qualification often requires significant effort and documentation, especially when tool versions update frequently.
That sounds like a lot of work, qualifying every tool update.
It can be. However, the standard also provides a pragmatic alternative to full tool qualification, which is often used in practice. Instead of formally qualifying the tool itself, you can choose to implement increased measures within your own development process, specifically designed to detect any potential erroneous outputs from that tool. This effectively reduces the tool error detection classification down to TD1, high confidence in detection, which, according to the standards table, can avoid the need for full tool qualification even if the tool has high impact, TI2. While this approach might increase the initial and ongoing development effort because you're adding additional verification steps like rigorously reviewing the tool's output, example inspecting generated code, or implementing extra redundant test steps specifically targeting potential tool-induced errors, it can significantly reduce the formal qualification burden, especially for tools that change often. The ultimate goal, whether through qualification or enhanced detection, is always the same: ensuring that any potential errors introduced or missed by the software tools are reliably caught and mitigated before they can compromise the safety of the final product.
Okay, this has been an incredible journey through the different phases of the functional safety lifecycle concept system, hardware, software. Now, let's truly connect all the dots, because it's clear this isn't just a series of isolated steps performed one after another. It feels more like a meticulously choreographed dance, maybe a grand symphony, as you said earlier, designed to ensure functional safety throughout a vehicle's entire development and operational life. How do all these pieces ultimately fit together to provide that final safety assurance?
You've perfectly captured the essence of it. It's not a relay race where one team hands off to the next and forgets about it. The true genius and strength of ISO 26262 lies in its emphasis on seamless flow, continuous feedback, and absolute traceability across the entire lifecycle. Everything must connect. It begins, as we discussed, with the HARA in the concept phase. This precisely identifies the hazards, assesses the risks, and defines those critical ASILs and the top-level safety goals. These form the foundation. These foundational safety goals then directly drive the creation of the functional safety concept, FSC, the what, which in turn leads logically to the more detailed technical safety concept, TSC, the how.
Right, the flow down the left side of the V.
Exactly. From there, the technical safety concept is systematically decomposed. This means breaking down those high-level technical requirements into increasingly granular system requirements. then hardware safety requirements, and software safety requirements, each with their corresponding detailed designs. And critically, at every single step of this decomposition, the design produced at a lower level is rigorously verified against the requirements imposed by the higher level it came from. For instance, the hardware design isn't just created in isolation based on the hardware requirements. It must be meticulously verified against those requirements and against the overarching technical safety requirements to provide undeniable evidence that it correctly implements the specified safety functions and mechanisms allocated to it. Traceability is key, linking evidence back up.
Verification at every step.
Absolutely. The process then builds back up through the integration and testing phases on the right side of the V model. We move progressively from verifying individual software units to integrating software components, then integrating software with the hardware, and finally rigorously testing the complete system or item, often within the vehicle itself. This progressive integration and testing ensures not only that all the defined safety measures are properly implemented in their respective domains, hardware, software, but also that they interact correctly together as intended, and most importantly, that the integrated item ultimately achieves the safety goals originally set out way back in that initial concept phase. Every layer builds upon the last, culminating in a confident, verified, and validated whole.
So it all has to come together and meet those original goals.
Precisely. And the ultimate culmination of all these efforts throughout the entire V model is safety validation. This isn't just another testing phase. It's a comprehensive demonstration performed at the end of the development, typically at the vehicle level. Its specific objective is to provide definitive, ironclad evidence that the top-level safety goals derived from the HARA are actually achieved by the integrated item functioning within the vehicle under representative real-world conditions. This involves a wide variety of tests and analyses, potentially including those extensive long-term endurance tests, targeted fault injection tests to ensure resilience against failure, and crucially, extensive user tests or field trials under real-life conditions that simulate every imaginable driving scenario and interaction. It's the final proof that the product is safe for its intended use.
The ultimate proof in the pudding, tested in the real world.
You could say that. So if we connect this all back to the bigger picture, it really highlights how functional safety, as defined by ISO26262, is fundamentally a continuous living process. It's a process of careful planning, systematic refinement, rigorous verification at each step, and comprehensive validation at the end. It's an iterative loop, constantly feeding back information, designed to ensure that risks arising from malfunctioning E-systems are systematically identified, assessed, and reduced to an acceptable, tolerable level at every single stage of development. It's truly about building safety in from the very beginning, not merely checking for it or trying to add it on at the very end. It's an ongoing, disciplined commitment to protecting people. Hashtag outro.
Wow. You've just taken us on an incredible deep dive into the, well, often invisible, world of engineering that ensures our cars are not just smart and powerful, but profoundly safe. Understanding ISO 26262, particularly the scope covered by Part 10 and the lifecycle phases we've discussed, truly reveals the immense depth of commitment and meticulous effort required to bring these incredibly complex, safety-critical EE systems to market. It's really a testament to meticulous planning, rigorous execution, continuous verification, and comprehensive validation, all working tirelessly behind the scenes for your protection every single time you get behind the wheel.
It really is.
Yeah.
And, this whole discussion raises, I think, an important and challenging question that the entire automotive industry is grappling with right now. As vehicles become increasingly automated, even autonomous, with AI potentially making real-time driving decisions and systems interacting in unprecedentedly complex ways, how will these established safety frameworks like ISO 26262 need to evolve? We've spent decades designing these processes primarily around preventing harm with a human driver involved. But what does functional safety truly look like when the human isn't always in the loop, or when the driver is actually an algorithm making probabilistic judgments? How do we ensure safety in that future?
That is a fascinating and, frankly, a bit of a mind-bending thought for sure. A huge challenge, and one that engineers and researchers around the world are grappling with every single day as we move towards that future. For today, though, thank you for joining us on the deep dive. We hope you've gained a new appreciation for the many layers of safety engineering embedded in your vehicle. Until next time, drive safely knowing there's a whole world of dedicated safety engineering working tirelessly behind the scenes just for you.